In this lecture, we introduce two basic concepts for the development of the theory of computational complexity: problems and algorithms. A problem, let us call it pi, is defined by a general description of its parameters and a statement of what properties a solution to the problem is required to satisfy. When we assign values to the parameters involved in the problem, we construct a specific instance of the problem. Let us fix the concept with an example. The traveling salesman problem, TSP for short, is a well-known problem in theoretical computer science and optimization. Suppose a salesman has to travel to different cities in the US in order to sell some products. Of course, his goal is to find a tour that allows him to visit all the cities while minimizing the total traveled distance. Formally, the problem has some inputs, which are its parameters, a list of cities C1, C2, Cm, and a distance d of Ci, Cj for every pair of cities Ci and Cj. Note that a particular list of cities, together with values for all the distances, define a specific instance of the TSP. The solution to the problem, that is, its output, is a tour tau of all the cities, formally an ordered list of cities, tau of 1, tau of 2, tau of m. It is assumed that the tour ends in the origin city, that is, tau of 1. The tour must satisfy the property that each city is visited once, and it must be a tour of minimum length among all the possible tours. For instance, in picture you see a tour of minimum length for the example instance. In mathematical notation, the TSP can be formulated as the minimization problem in the yellow rectangle. Another important concept is that of algorithm. An algorithm for solving a problem pi is a general, self-contained, step-by-step procedure that takes as input an instance of pi and produces as output a solution for that instance. Let us consider again the TSP. An if algorithm for solving the TSP is based on the enumeration of all the possible permutations of cities, that is, all the possible tours, while computing the length of each of them. Then, a solution is simply obtained by picking a tour with smallest length. For instance, consider the instance in picture, where colored dots are the cities and the distances are the real geographical distances. The naive algorithm would enumerate all tours. Say the first one is C1, C2, C3, and C4 with total length L1. Then C1, C2, C4, C3 with length L2, going on C1, C4, C2, C3 with length L3. As you can imagine, this approach is not feasible as the number of possible permutations of cities that you have to enumerate is huge, even if your problem involves a small number of cities. To be precise, there are n factorial permutations where n is the number of cities. The question now is whether the TSP admits an efficient algorithm or not. We will answer this question later, exploiting the theory of NP-completeness. In order to analyze the performance of an algorithm, we need to introduce a formal computer model. In theoretical computer science, the most used model is the Turing machine, invented by Alan Turing in 1936. A Turing machine is an elementary model of computer. It has a memory, a tape made of infinite memory cells. Each tape cell can contain a symbol, and symbols belong to a given finite alphabet. The machine has a tape head that can move along the tape from left to right, and it can read and write symbols. The Turing machine is controlled by an internal processing unit, which is defined by two elements. The first one is a finite set of states. The Turing machines that we are discussing here can be in only one state at a time. For this reason, they are said to be deterministic. There is a special state that is called initial state, and it is the one where the machine begins its computation. Then there are two terminal states where the computation stops, one corresponding to answer yes, and another one corresponding to answer no. As a result, the model we are describing here can only produce a binary output, either yes or no, 1 or 0. Of course, extension of this model can output more general strings of symbols, but they are outside the scope of these lectures. Finally, the second element of the machinery controlling a Turing machine is a table of rules, which define the transitions from one state to another state. Specifically, a rule applies when the machine is in some state and under the tape head there is some symbol. And it defines which is the new state, the symbol that the tape head must write in the current tape cell, and the movement that the head must perform, either going one cell on the left or one on the right. Of course, in a deterministic Turing machine, there must be at most one applicable rule in any possible situation, as the next state must be uniquely determined. In conclusion, the Turing machine starts from the initial state, with some input represented as a string of symbols stored in the tape. It performs a sequence of steps following the rules in the table, and it halts when it reaches a terminal state, either with answer yes or answer no. As a result, you can think of a Turing machine as a formal model of an algorithm. In order to evaluate the performance of an algorithm, we will use two measures. The space complexity is defined as the overall amount of memory which is required by the algorithm. Formally, it is the maximum number of tape cells which are used by a Turing machine that executes the algorithm. The time complexity is the running time needed for the execution of the algorithm. In formal terms, it is the number of computational steps performed by the Turing machine running the algorithm. How can we compute these quantities? In these lectures, we will focus only on the time complexity. Given an instance I of a problem pi, the size of I is the number of symbols needed to describe I in some given encoding scheme. An encoding scheme describes how an instance can be represented with symbols drawn from some alphabet, usually the binary alphabet, where symbols are either 1 or 0. We will use n to compactly denote the size of a problem instance. The time complexity of an algorithm solving pi is formally defined as a function t of n, which maps every size value n to the running time of the algorithm when it is applied to an instance of size n. Since the running time may be different from different instances having the same size, usually the worst-case running time over all instances of size n is taken. It is often the case that the derivation of an explicit expression for t of n is not trivial. As such, usually only an upper bound on t of n is provided, using asymptotic notation. Recall that we say that t of n is big O of some function f of n if, for sufficiently large values of n, f of n dominates or bounds above t of n. That is, t of n is less than f of n scaled by some constant c for all n greater than some threshold n0. This is an example of functions f of n and t of n, such that t of n is big O of f of n. An important distinction when talking about the time complexity of algorithms is the one between polynomial and exponential time algorithms. An algorithm is polynomial if its time complexity t of n is big O of n to the power of d, where d is a constant. That is, its running time is bounded above by some polynomial function. Below you have an example. An algorithm is exponential if its time complexity is big O of an exponential function. As you can imagine, in practice, polynomial algorithms run much faster than exponential ones, on instances having large sizes. So, when facing a new problem, the best you can hope for is finding a polynomial algorithm that solves the problem. However, a polynomial algorithm may be worse than an exponential one. For instance, when the degree of the polynomials involved are high. If this is the case, an exponential algorithm might perform better than the polynomial one on instances of small size. We conclude with some considerations. The first one is about why it is reasonable to assume that algorithms are run on a Turing machine. Indeed, modern computers are more sophisticated and have much more computational power than Turing machines. However, it can be proved that, for the purpose of the theory of computational complexity, any model is fine, provided that it is reasonable, which means that there is a polynomial bound on the amount of work that can be done in a single step of the computation. Thus, for simplicity, theoretical computer scientists focus their attention on Turing machines. The second consideration is about encoding schemes. Is the choice of the encoding scheme relevant? Does it affect the theoretical results of the theory of computational complexity? The answer is no, provided that the encoding scheme does not use unnecessary symbols. For instance, it does not add useless paddings, and numbers are represented with a reasonable encoding, for instance, binary rather than unary.